Welcome to Part 17 of Applied Chemistry, where we'll explore polymers. Polymers are macromolecules composed of repeating units, known as monomers, linked by covalent bonds to form long chains. Due to their versatile properties, polymers are found in a wide range of applications, from packaging materials to advanced technologies in electronics and medicine. We can classify polymers based on different criteria, including source, structure, and the mechanism of polymerization. These classifications help us understand how polymers behave and determine their best applications. Polymers can be grouped by their source as natural polymers, found in nature, like cellulose in plants and proteins in living organisms. Synthetic polymers, man-made for specific uses, such as polyethylene and polypropylene. Semi-synthetic polymers, derived from natural polymers but chemically modified, like cellulose acetate used in photographic films. Structurally, polymers can be linear, consist of long, straight chains, which increase strength due to stronger intermolecular forces. Branched, have side chains, resulting in greater flexibility. Cross-linked, contain chains connected by bonds, forming a network structure that enhances durability, like vulcanized rubber. Polymers form through two main mechanisms: addition polymerization. Monomers with unsaturated bonds join without creating byproducts. Condensation polymerization. Monomers react, releasing small molecules like water as byproducts, as seen in nylon and polyester synthesis. Polymer functionality refers to the number of bonding sites on a monomer, which affects the polymer structure. Monofunctional, one bonding site, forming simple chains. Bifunctional, two bonding sites, creating linear or branch structures. Polyfunctional, multiple sites, leading to complex, cross-linked structures, like those in phenol formaldehyde resins. Plastics, particularly polyethylene and vinyl-based plastics, are used extensively in consumer products and industrial applications. Let's explore their synthesis, properties, and common uses. Polyethylene is the most widely used plastic globally, comprising a family of thermoplastic polymers made through the polymerization of ethylene. LDP is produced via free radical polymerization of ethylene at high pressure. Its branch structure gives it flexibility, lower density, and resilience. Applications include plastic bags, films, and flexible packaging due to its durability and transparency. HDP forms through low-pressure polymerization with catalysts, creating a linear structure with high density, rigidity, and resistance to chemicals. It's widely used in products like milk jugs, detergent bottles, and pipes due to its strength and impermeability. LLDP results from copolymerizing ethylene with longer chain alkenes, offering higher tensile strength and puncture resistance than LDP. It's ideal for stretch films, bags, and other packaging requiring flexibility. UHMWP has extremely long polymer chains, making it durable, impact-resistant, and low friction. Commonly used in medical implants, bulletproof vests, and high-performance gears, UHMWP is valued for its superior mechanical properties. Vinyl plastics are a diverse category, with widely different applications and chemical structures. Nylon is synthesized through a polycondensation reaction between diamines and dicarboxylic acids. It's known for strength, durability, and flexibility, making it ideal for textiles, automotive parts, and mechanical components. Phenol formaldehyde resins or bakelite. Formed by condensing phenol and formaldehyde, bakelite is a highly heat-resistant and durable plastic. Its applications include electrical insulators, kitchenware handles, and adhesives, given its excellent insulation properties. Glyptyl is a resin formed by reacting phthalic anhydride with ethylene glycol. Known for its adhesive and durable properties, it's commonly used in paints, coatings, and sealants, providing resilience and stability. Specialty polymers are engineered for high-performance applications, possessing properties like enhanced thermal stability, conductivity, or biodegradability. They're used in fields such as electronics, healthcare, aerospace, and environmental protection. Engineering thermoplastics offer durability, resilience, and precision, making them essential in demanding applications like automotive, electronics, and consumer goods. Their high strength-to-weight ratio makes them ideal for structural and mechanical uses. Engineering thermoplastics include polycarbonate, PC, transparent and impact-resistant, used in eyewear and electronics. Polyamide, nylon, durable and flexible, common in textiles and gears. ABS, tough and used in automotive parts and appliances. PEEK, known for thermal stability, used in aerospace and medical devices. Conducting polymers can carry electrical current, making them valuable in electronics and energy devices. Key properties include flexibility, environmental stability, and varying conductivity based on the level of doping, enhancing their versatility. Conducting polymers possess electrical conductivity, modifiable by doping. Flexibility. They're easy to shape and integrate into wearable electronics. Environmental stability. Some resist corrosion better than metals, making them ideal in challenging conditions. Examples include polyaniline, poly, and polypyrrole, PP, widely used in batteries, sensors, and anti-static coatings. These polymers are also essential in creating lightweight, flexible electronic devices like solar cells and biosensors. Electroluminescent polymers are organic compounds that exhibit electroluminescence, making them suitable for display technologies. Electroluminescent polymers emit light when an electric current passes through. This property makes them valuable for OLED displays, flexible screens, and lighting solutions, providing advantages in flexibility, energy efficiency, and vibrant colors. Liquid crystalline polymers are unique materials that possess both liquid and crystalline properties. LCPs are known for their high thermal stability, chemical resistance, and strength. Applications include electronic components and lightweight, strong parts in automotive and aerospace due to their exceptional durability. They have ordered molecular structures that can flow, making them highly valuable in applications requiring strength and flexibility. Biodegradable polymers decompose naturally in the environment, reducing plastic waste and pollution. These polymers are increasingly popular due to rising environmental concerns. Biodegradable polymers decompose naturally, reducing environmental impact. Types include polylactic acid, PLA, made from cornstarch, used in packaging and medical implants. PHA, bacterial fermentation-based, compostable, used in packaging. PCl, flexible, low melting point, used in medical devices and biodegradable blends. Biodegradable polymers are mainly used in packaging, agriculture, and medical devices. They're also being explored for controlled drug delivery, taking advantage of their predictable degradation rates. We've reached the end of this video. Thank you for watching, and don't forget to like and subscribe for more tutorials on applied chemistry and other exciting topics.